Welcome to Exploratory Problem Set 2-1. Problem number 1, exponential function problem. In the exponential function, f of x is equal to 0.2 times 2 raised to x, where f of x could be the number of thousands of bacteria in a culture as a function of time, x, and hours. Find f of x for each hour from 0 through 5. Plot the points and graph the function as in figure 7-1b, or the figure that you see here at the right. How do you interpret the concavity of the graph in terms of the rate at which the bacteria are growing? So first, we have to create a table, of course. So this is our table. Okay. And let's create the x and y values from 0 to 5. Okay. I think we have a bigger table than we have to, but then it's okay. So now we will have our values for x and y. So the problem says that we have to include values of x from 0 to 5. So let us do that. 0, 1, 2, 3, 4, 5. Okay. And our y here would be, what is our y here? If x is equal to 0, this is our function. This is our function. So if x is equal to 0, then our y would be equal to 0.2. If x is equal to 1, it would be, our y would be 0.4. If x is equal to 2, then our y would be 0.8. If our x is equal to 3, then our y would be equal to 1.6. If x is equal to 4, then that would give us 3.2. And if x is equal to 5, that will give us 6.4. Okay, now let's take a look at the graph. Okay, now let's position this one to, let's position this to a better location for this one. Okay. Say, let's put it here. Okay, it's perfect. And let's put our graph here. So as you would notice, from 0 to 5, the points are already laid out. You could see here, okay, from if our x is equal to 0, now let's open the grid for you to be able to read it properly. Okay, if x is equal to 0, you could see that our y is equal to 0.2. If x is equal to 1, it's 0.4, 0.8, that's 1.6, 3.2, and we lastly we have 6.4. Okay, now let's take out the grid lines. Okay, so the question here is, we have already plotted the points and we already have graphed the function. So how do you interpret the concavity of the graph in terms of the rate at which the bacteria are growing? So as you can see, the concavity of the graph is seemingly like this. So it is actually going exponentially, and the concavity is upwards, right? the concavity is upwards, so it's concave upwards. Okay? So the bacteria, what do you call this? The bacteria grow in terms of a concavity which is going up, so it's increasing exponentially through time from 0 to infinity. So as you can see, from x is equal to 0 to x is equal to 5, it already, what do you call this, created or have given a pattern that increases exponentially through time. So this is our answer for number 1. Exercise number 2, power function problem. In the power function g of x is equal to 0.1 x cubed, g of x could be the weight in pounds of a snake that is 8 feet long. So g is, what is our g? G is the weight in pounds. So notice it is in pounds of a snake that is x feet long. Okay? Plot the points for each foot from x is equal to 0 through 6 and graph the function g. Because graphs of f in problem 1 and g in problem 2 are both increasing and concave up, what graphical evidence could you use to distinguish between the two types of functions? Is the following statement true or false? The snake's weight increases by the same amount for each foot it increases in length. So we have a lot of questions in the problem, but we have to single them out. First, we plot the points for each point or for each foot from x is equal to 0 through 6, and we're going to graph the function. That's our first requirement. So how do we graph how do we start it? Of course, we have to start it by plotting the points. So we get the points. Okay? Let us have the points. Okay, let's create a table first, of course. So we will create a table, okay, for our x and y. Okay, now I am drawing the tables, the table for our x and y for the following power function. Okay, perfect. So we will have x here on the left side. Okay, this is our x, and this would be our y. So our x would be from 0 through 6. So 0, 1, 2, 3, 4, 5. We need one more table. Okay, but I think I will just adjust this. So x and y would be here. So this is my x, and this will be my y. Okay. And 0 through 6, 0, 1, 2, 3, 4, 5, 6. And then we have our y values. If x is equal to 0, then we have to make use of our calculator again. Let's have the calculator. Okay. If x is equal to 0, that would have g of x is equal to 0.1 times 0 cubed, so that would be 0. Am I correct? Okay. If our x is equal to 2, we have 0.1 times 2 raised to 3, or that would give us 0.1 times 8. So 0.1 times 8 gives us 0.8. So 0.8. What if our x is equal to 3? 0.1 times 3 raised to 3, so 0.1 times 27. So 0.1 times 27 is equal to 2.7. If our x is equal to 4, we will have 0.1 times 4 raised to 3. So we would have 0.1 times 64. 0.1 times 64 is obviously 6.4. If we have x is equal to 5, we will have 0.1 times 125. So 0.1 times 125. And that will give us 12.5. If our x is equal to 6, we would have 6 raised to 3 times 0.1. So 0.1 times 6 raised to 3 is equal to, let us see that. 6 times 6 times 6 is equal to 216. So we just multiply it by 0.1. It will give us 21.6. So now we have created the values for x and y. And we get rid of this calculator here. Okay. And then we plot all of these points on the right side. We already have the x-axis and the y-axis here. So if our x is equal to 0, then our y is equal to, I think I overlooked something. I just noticed it now. So let's remove. This one should be on top of our 1. So it would be 0 here, and then 0.1 times 1 cubed, that's just 0.1. Okay. And to your right are the laid out points for this function. So let us just arrange them properly into the grids. So as you can see, if our x is equal to 0, our y is also equal to 0. If x is equal to 1, y is equal to 0.1. Y is 0.8 for x equals 2, and so on and so forth. So we have already satisfied the graphing. So we already graphed the function g from x is equal to 0 through 6. And as you can see in problem 1, so let's take out the grids. In problem 1, this is your problem 1, this is concave up and increasing, right? Now in problem 2, let's see, it's somewhat the same. So let us connect all of the dots to exactly see through the pattern of this graph, how this graph goes. So let us investigate. Okay, let us connect all of the points. So I'm connecting this here, here, up to the end. So from 0 to 6, it would look like that, with the points, with the distinctive points here. These are my distinctive points. This, and origin. So as we can see here, this is also concave up. So the concavity is still upwards. And it is also increasing. So the slope is increasing, meaning that the value of your g of x as x goes by for each foot, so let's say x is equal to 7, will always tend to rise upwards, or your g of x will go like adding more pounds of the snake. That is, for example, 7 feet long, then the weight of your snake in pounds will be greater than 21.6 pounds for our 6 feet of a snake. So where are we now? we are here, right? So we have compared them, and as you can see, they are like similar. So similar because we have the same concavity and the same trend increasing. Okay? So the question here is, what graphical evidence could you use? Yeah, this is an interesting part, okay? Because what graphicals, because they are seemingly similar. Okay? They are seemingly what do you call this? Like twins. But of course there is a distinction between the two. And what is that? Now let us take a look again at the previous function. This is our previous function. And I have told you that this previous function is concave up, but look at its trend here on the tail from 0 going to the left. So let's investigate further what's going on from x is less than or equal to 0. So let's have an analysis on this portion. Let's draw. Okay, I don't need these colors. Okay, I should pick another color. So let's say I like this color. Okay. So let us have this graph. Okay. Now let us investigate what goes on when your x is less than 0. So let's see. If my x, this is my x, and this is my y. If my x is equal to -1, for example, and -2, -3, -4, -5, and so on and so forth. But I would want to get my values for y from -1 through -5. So let's make a use of the calculator again. Calculator is very helpful in this time of need. So using the same function, f of x is equal to 0.2 times 2 raised to x. Our y for x is equal to -1 would be -1, or 0.2 times 2 raised to -1 is equal to 0.2 times 1/2. So that's 0.2 divided by 2. So we would have 0.1 here. This is 0.1. What about when our x is equal to -2? When x is equal to -2, that would be 0.2 times 2 raised to -2, so 0.2 divided by 4. So 0.2 divided by 4, that's 0.05. And if it's 3, so 0.1, 0.2, sorry, 0.2 divided by 8, then we give you 0.025. If x is equal to -4, you have 0.2 divided by 16. That would give us 0.0125. And if our x is equal to -5, so 0.2 divided by 32, that would give us 0.00625, and so on and so forth. Now, as you can see, your x is being approached, but the curve does not touch the x-axis. So we already discern that as our asymptote. So for exponential function, we have a certain asymptote wherein the graph approaches that certain limit or asymptote, but will not cross that value. So in this case, this graph cannot cross the x-axis because that is the asymptote of the exponential function f of x is equal to 0.2 times 2 raised to x. Whereas on the power function, so these are functions with certain powers like x raised to 2, but that's quadratic function already, so we begin the power function from x cubed to x fourth to x raised to 5, or those exponents that are greater than 2. So in this case, look at the trend of our graph when it goes from x equals 0 to the negative part. So let's investigate for us to be able to, let's say, create or have an impression of the distinction between the power function and the exponential function. Let us have values again for x and for y. And this time I'm only going to consider 4 values of x which are negative. So this is my x. This is my x and this is my y. So x is negative 1, negative 2, negative 3, negative 4. Okay, we don't consider these 2 remaining tables here. So if x is negative 1, it is obvious that it's negative 0.1 for y. So y is negative 0.1. If x is negative 2, then that would be negative 8 times 0.1, so negative 0.8. If x is equal to negative 3, so that would be negative 2.7. If x is equal to negative 4, then it's negative 6.4. So look at how the transformations happen. In this case, okay, let us group this. In this case, what happens is that if we are going to graph these values, it would just be the negative opposite of our values of y from 0 to 6, or from 1 to 6 rather. So this will give you a reflection which is, this is too thick, which is something like this. So this is the reflection. And the concavity now is downwards and it is decreasing. So that's the distinction between the exponential function and the power function. Okay, let's arrange the tables. Okay, so I hope you understood much better what an exponential function is with respect to the power function. So is the following statement true or false? The snake's weight increases by the same amount for each foot it increases in length. Yes, it is. As I have told you, this is a power function wherein every foot you add to the length of the snake will give to an increased, a cubic increase of the pounds of the snake. So as you can see, the graph is here, and it's an evidence. It is actually the evidence. So this is our x is equal to 5, and x is equal to 6 will be a lot higher. So x is equal to 6 would be there, right? Okay, so as you can see, the points here goes to that point, and so on and so forth. So this is a power function wherein it has a concavity of an upward position. It goes up, okay? It opens upward. The concavity opens upward, and it is also increasing. So this is the complete solution for example number 2, or exercise number 2. Thank you for watching.